Zanderighi from CERN and the University of Oxford. She will talk about high precision QCD and LHC.
Okay, thank you very much. So what I will do is I will start with a sort of a little bit general introduction about the LHC and then we'll move on and later to discuss sort of high precision calculations in QCD. So everybody is familiar with the Large Hadron Collider experiment. This is just shown here just to show the size of the experiment, for instance, compared to the airport in Geneva or to the lake. And so in a nutshell, it's very easy to quote impressive numbers about the LHC, both in terms of energies, magnetic fields, number of dipoles, temperatures at which it operated. And so the first run happened at 7 and 8 TeV, and here about 25 inverse femtobards of data were collected. This is really 25 trillions of proton-proton collisions collected, really, so really quite a lot. Now the upcoming run 2 will be at 13 TeV and will happen next year. Now there are 4 main experiments, Atlas and CMS, which really focus on Higgs studies and on high PT new physics searches. And I will spend most of my time working on this. And then there is also LHCb experiment with flavor physics, CP violation, and heavy quark physics. And others were the main heavy ion collisions and studies of quark plasmas, so the main themes. Now we know that the status of particle physics, we know that the Standard Model is a very successful theory in describing strong, weak, and electromagnetic interactions. On the other hand, we know that it's not a fundamental theory. So there are sort of theoretical issues, but really, I believe most importantly, there are really unexplained phenomena. For instance, gravity cannot be accommodated, the matter-antimatter symmetry that we observe, dark matter, dark energy, and so on. So the LHC was designed to explain electroweak symmetry, so explain the origin of mass in the Standard Model and find the new physics. And of the two, the LHC was essentially now successful in this first item. Now, before moving on, I would like to really discuss well, we know what this really means. So what is the issue with electroweak symmetry breaking, and what is the problem with particle masses in the Standard Model? And also, why did people believe that they should be reading new physics at the TeV energy scale, so at the energy scale really explored by the LHC experiment? Now, to do this, let's take a big step back and go back to really quantum field theory. We know here that there is a duality between particles and waves. So, for instance, to the electromagnetic wave, we associate a particle which we call the photon. And so we know that if you have a source that emits photons in a given direction, photons have two polarization states. So there is a magnetic field and an electric field that are transverse to the direction of propagation. This is essentially, it's an empirical fact, but it's really crucial. So why is that? Well, it's crucial because if a third polarization existed, so if the photons would be longitudinally polarized as well, you would see that you can have scattering probabilities that grow with the energy scale. This means that whenever, at some point, if you increase the energy, at some point you have probabilities larger than 1. This means that you are violating unitarity. This cannot happen. And this tells you that your theory simply breaks down. So in QAD, it does not happen. So we know that the photon does not have a third polarization state. And this is really related to the gauge symmetry of QAD. Right. So the gauge symmetry, if you want acts like a filter, it takes away this third polarization state. So you're left with photons which have two states. And this then is really crucial to keep your theory sensible even when you go to high energies. On the other hand, we also know that the speed of light of these photons is the same in any reference frame. Whether you sit, move slowly or fast, you always observe the same speed of light. Whenever you have a massive particle, this is not the case. In particular, what you can do is you can also always go in a frame where your massive particle is at rest. If your particle is at rest, you can't distinguish between longitudinal and transverse polarization states anymore. This means that you can't, at this point, by definition, this distinction breaks your rotational invariance. So clearly, your gauge trick does not work whenever you have massive particles. On the other hand, we know from LEP, LEP was an experiment that ran essentially between 1990 and 2000, again at CERN, where E plus E minus collisions happened actually even lower than this, but in a quite broad energy range. And we know from this that WZ interactions are described by a gauge theory, and that they have a mass that breaks the electroweak symmetry. So essentially we will find that the theory then breaks down at high energy because of this. And one can compute, for instance, WW scattering. You have longitudinal degrees of freedom there. You must have them because the particle is massive. And you can see at what energy does your theory breakdown. And you find that this really happens at about 1 TeV. This is why this 1 TeV energy scale was really crucial. So the LHC was then really designed to investigate how you can generate these masses and all other masses in the standard model and still keep your theory sensible at high energies. And so the most popular mechanism, which probably you know very well, is what is called spontaneous symmetry breaking. So what does this mean? It means that essentially you have a theory that has some symmetry, but the solutions to the configurations break your symmetry. So this is, for instance, shown here. You have, for instance, some law that has some rotational invariance, but once you pick a given configuration, so the configuration breaks the rotational invariance, but your laws of physics still obey this symmetry. This is what is called the spontaneous symmetry breaking. Now, a typical thing about spontaneous symmetry breaking is that whenever you have an exact symmetry, for instance, you could have two particles, an up and down quark, that have solutions where the two masses are the same. With spontaneous symmetry breaking, you can also have solutions where one of the quarks, for instance, is more massive than the other one, or one is heavy, one is light, as long as the other solution also is allowed. So typical of the spontaneous symmetry breaking is sort of degeneracy of solutions. And this is the usual potential that you're probably familiar with. And you see that here you have a lot of degenerate solutions. Essentially, you can move around this direction, all the states are degenerate, and it takes no energy to move around. What this means is that to those states, it corresponds to so-called massless particles, because you don't need any energy to go around this direction. So the prediction is that there should be a massless Goldstone boson. And on the other hand, in the electroweak theory, we don't observe these bosons. And so in the Higgs mechanism, this zero energy excitation is essentially absorbed into the gauge field. So what the result of this is that you start from bosons that have only two longitudinal degrees of freedom and no Goldstone boson, and you end up with massive gauge bosons with three physical polarizations and with no Goldstone boson. And so in this picture, then the Higgs field, if you want, acts like a medium. So particles without Higgs field would propagate at the speed of light. Then the Higgs sort of acts like a medium, so it slows down particles, so they essentially acquire a mass. This velocity is not the speed of light anymore. So to summarize, essentially, the problem was that if you have massless particles, you have gauge invariance and no unitarity violation. With massive particles, you have this unitarity violation. So what the Higgs mechanism does is, if you are at the small energies or large distances, you feel this Higgs field. So your states are massive, but at high energies you don't feel it and you don't have unitarity violation. So it's sort of smooth interpolates between these regimes. And of course, if the Higgs field exists, there are also quanta of this field, so the Higgs boson. And also the Higgs boson then essentially interacts with itself. And the interaction, so then the mass of the particle, they slow down proportional to this interaction, tells you that the mass of all particles are essentially proportional to the coupling of the Higgs. So in fact, in the standard model, what then happens is that you have one additional free parameter, the mass of the. So once you know the mass of the Higgs boson, you essentially know this type of coupling, and this is then the same for all particles. So in the standard model, this Higgs mechanism is very nice because it's very predictive. If you know the mass of the Higgs, you know everything. It's the only three parameters. And you know, this was essentially really a milestone for particle physics. The Higgs boson was discovered in the LHC, It was announced on the 4th of July 2012, and it was seen immediately really in many channels. So what is shown here, for instance, this is the mass of gamma-gamma. So this is a Higgs decay into two photons. This was a channel that was believed to be really very difficult because essentially you have a huge background and a little peak on top of this. But because it's so clean, you see that you can subtract the background and really see a nice peak. And then similarly you have ZZ, where the Z is equal to 4 leptons, or WW. In the case of WW, because the W is decaying to neutrinos, you can't reconstruct the mass directly, but you can look at things like the transverse mass shown here. So it was immediately seen in several channels, and it led to a Nobel Prize in physics the year after that. The other thing, on the other hand, is that once you see a Higgs, you realize that you have a so-called hierarchy problem. So what is this problem? Well, you know that the Higgs mass, so if you think about the Higgs propagator, it receives corrections from essentially fluctuations, from vacuum fluctuations. And the size of those corrections, because this is a scalar, it's not protected by any symmetry, the size of the corrections have essentially no cutoff, so a proportion to the maximum allowed energy that you have. So the fact that the mass of the Higgs that we observed, 125 GeV, is much smaller than, for instance, the Planck mass, really requires what is called fine-tuning. And if you want to think of an analogy in terms of thermal fluctuations, you could think of put a particle in a thermal bath. Now, if you wait for a long time, even if this has a different energy at the beginning, if you wait long enough, at some point you should expect that this particle has roughly the same energy of all the other ones. While what we observe is that this red particle has an energy that is 10 to the 17 times smaller than all the other ones. So while one cannot say this is inconsistent, it's hard to believe that this happens without there being a good reason for this. So what would you think of a good reason here for this red to be sort of so much smaller energy than blue? The natural explanation here would be that, okay, red essentially cannot interact with blue, so there is some screening, so that red is screened from these interactions. And this is also what we do in particle physics, right? So you can say that this interaction is screened by some new forces over some new particles. And in the last years, lots of new physics models were suggested to sort of explain precisely this hierarchy problem. And well, the idea is essentially that you have some new physics states that essentially screen or cancel this type of effects. And of course, all these type of new physics models are sort of speculations. What you need are always data from the LHC to discriminate and to exclude models. And so at the LHC, a few years ago, there was really a lot of hope to sort of see new physics directly. So the hope, for instance, if you do SUSY models or extra-dimensional models, was that essentially at some point you have enough energy to produce some massive states, for instance, squarks or gluinos, and that those then decay into some standard model particles and possibly missing energy. So the type of processes that people concentrated on then were sort of high multiplicity final states, where typically you have maybe lepton, missing energy, and many jets in the final state. And a lot of effort was really put to then sort of have standard model calculations for these high multiplicity final states, because these are backgrounds to this type of processes, and you want to subtract the background accurately. So for instance, for something like this, a background would be W plus 3 jets. So you have a lepton, missing energy, and 3 or 4 jets, and so on. Now, how do you improve precision on the standard model backgrounds? What we can do is we exploit the fact that in QCD, but also in electronic theory, the coupling constant is small. For instance, the QCD coupling constant is about 0.1 at 100 GeV. Electroweak is even smaller, about 10 times smaller. And so if the coupling constant is small, you can take a cross-section and expand it in powers of your coupling constant. Then you have a leading order prediction here divided out. This becomes then your leading order result. Your next to leading order result is suppressed by 1 power of this alpha. The next to has 1 more power of alpha and so on. So what you expect is that the more terms you compute here, the more precisely you can predict your cross-section. The other thing that one can do is, in some cases, there are sort of large logs that appear, and it's possible to understand where they come from, and it's possible to resound them to all orders. So what people have been doing are so-called leading log, next to leading log resound calculations. So for instance, you introduce a sort of hierarchy in terms of alphas and logs, and you resound all these terms, and you miss terms that have one log less than all the other ones, but you resound terms to all orders in the coupling constant. And essentially because those logs have a sort of well-defined physical origin. Essentially, in many cases, they come from the emission of soft and collinear gluons. So instead of having to do a full calculation like you have to do here, you can essentially just simplify your matrix elements and then factorize things, exponentiate, and so on. And the third approach that is very important. So all you do here always has to do only with quarks and gluons. We know that we don't never observe quarks and gluons. What we observe are pions, mesons, and so on. So there are Parton shower event generators. What they do is, again, they use this type of approximation used here. So instead of using full matrix elements in QCD, they use the soft collinear approximation to emit many quarks and gluons in a probabilistic way. And at the very end, they have a sort of hadronization model, so they turn these many quarks and gluons at this point into hadrons. So those tools are called Parton shower event generators. So these essentially, these three things are the three main things that we have that we use to do precise calculations in QCD. And of course, there is a crosstalk between all these three objects. Now, I'd like to talk a bit more about next to leading order calculations. So, the point is that if you do a leading order calculation, you have typically large theoretical uncertainty. So let me just show one result here. This is, for instance, W plus, W minus, plus tau jet production. This is a very important background to Higgs in the channel Higgs to WW. What is shown here is the leading order cross-section at, for instance, 7 TeV as a function of your normalization and factorization scale. So typically, this is something we discussed before. Typically what you do here, you vary your scale in some range, and you see that the leading order prediction changes quite a lot. While at next to leading order, you really get a much sort of flatter curve. Then typically you say, okay, the fear uncertainty is what you get by varying your scale by a factor 2 up and down. So at next to leading order, the effect is that you reduce your theoretical uncertainty. This is also shown here. You can take things and look at what happens at higher energies. Again, here the scale was chosen, for instance, twice the W mass, because the Higgs goes into 2 onshell W's here. You vary your scale, you see that at leading order you have a large uncertainty, and next to leading order really much smaller. So this is a typical, and you can do this for different, you can look at plots like this for really all processes. These shapes are very different, very process dependent, but typically what happens is that NLO, your theoretical uncertainty is smaller. And because, I mean, it was really recognized that this is a very important issue, having next to leading order predictions, this was really a lot of work. So typically there were meetings in Lesuche in 2004, 6, 8, and so on, and people formulated processes that were considered priorities for LHC physics. I don't know if you can read, this is, for instance, PP two vector bosons and Bejet, Higgs plus 2 J, 3 vector bosons, here processes with 4 particles. And so they were sort of considered priorities for the LHC physics program. This was the last of this list in 2008. Now, how do people do NLO calculations? Well, we know how to do them since really times of essentially Feynman. All you do is you can draw your Feynman diagrams, you plug in your Feynman rules, you manipulate your amplitudes. Typically you have then loop integrals, here you can have loops, so you have to simplify these loops. So you get tensor integrals, which then you have to reduce to scalar integrals. But there are since really the time of Passarino-Weidman, there are very systematic procedures on how you go from a tensor integral to a set of scalar integrals that you know analytically. So in principle, this was a problem that was solved really many years ago. But practically, things don't really work when you go to high multiplicity. Essentially for 2 reasons. the number of Feynman diagrams that you have to go starts growing factorially. The terms that you obtain once you start doing this strength reduction also grows factorially. And practically what happens is that you get really large expressions, and then you have really numerical instability. So even if you try to program this brute force, what happens is that you really have large cancellations, gigantic cancellations, and your final result then completely misses precision. So in the years between 2004 and 2014, I think that's the last 10 years, really, there were a lot of breakthrough ideas on how to do NLO loop calculations without really computing loop diagrams. Essentially, mainly using generalized unitarity. So mainly the idea is that instead of computing loop diagrams, you cut these diagrams and then you reproduce one loop amplitudes essentially as products of on-shell tree-level amplitudes. So you move the problem from being one loop to only tree-level, products of tree-level on-shell amplitudes. And there are many techniques, many improvements, and many things. So here, this is a review of now a few years ago, which really sort of works out some examples on these unitarity methods, if you're interested. And just to show some of the breakthrough in technology, if you use Feynman diagrams, so what people often look at are pure gluon amplitudes. It's not really because it's particularly interesting. If you have a pure gluon amplitudes, you only have jets in the final state. And this is not a clean process at the LHC. Multi-jet production is the most complicated one because you don't have a lepton to take, you don't have instant energy, so it's not particularly important. But it's a sort of playground for theorists. So what is shown here is, in terms of the number of gluons, this is a 4 gluon amplitude, 5 gluon amplitude, 6 gluon amplitude, computed sort of using more standard techniques. And this is what one could then do using these unitarity-based techniques. You can really compute all of them because you can program something that is efficient and stable even at high multiplicity. And of course, okay, this is a playground, but this has been really applied to processes of interest at the LHC. And so this type of list is something that is now really closed. So now there's still work that's being done. So mainly on two directions. One is to sort of have something that is really completely automated. Not only QCD corrections, also electroweak corrections, and in principle something like MathGraph-like, also for new physics models. Really like MathGraph-like, for instance, in terms of the smart loop. And then there are other groups that sort of focus on really pushing even more the multiplicity. Doing phase-space integration is still difficult, so here you still use also analytical techniques to sort of improve the accuracy of your results. And just to show now that things are in fact really automated, this is now list of processes. So this is, for instance, vector boson plus jets. You see W boson, Zs, photons. Vector boson pairs plus jets. You see a huge list of things. And one can move. So this is all taken from one paper now. 3 vector bosons and a jet, 4 vector bosons, heavy quarks and jets, heavy quarks and vector bosons, single top plus other things, single Higgs pair production, heavy quark and jets. So the reason I show this list is to show you that, in fact, things are really automated. A few years ago, each of these lines would have been a separate paper. Right? People publish papers on, for instance, 4B production at NLO and so on. And now things, in fact, are really automated. Still, you see that the multiplicity can't be too high. I mean, if you go to high multiplicity, still you need a lot of computer power. But things are really automated. So this is the last, top quarks and bosons. And you see roughly the edge of what can be done. TT bar plus 2 vector bosons, for instance.
Sorry, Giulia, when you say automated, it runs on a laptop?
No, it runs on a farm. But you don't have to be an expert on the calculation. You take a code, you download it, you understand how to use it, and according to the process, I mean, a very simple one runs on a laptop, but the most complicated ones run on maybe 100 processors. But the thing is that you don't have to have any expertise to be able to use it, like MathGraph. Okay, so NLO is sort of automated. Now, what are still issues with NLO calculations? One is what we discussed a little bit here, this choice of renormalization and factorization scale. So what's the issue here? So take one of these processes, W plus 5 jets. What is shown here is the energy of the second jet. So you can, between 0 and 500. And what is shown here, this is the leading order prediction, blue, and this is the NLO prediction. This is a logarithmic scale. So here you see that at high energy you have gigantic negative corrections. And what you see here is the same plot, but with a different scale choice. Here the scale choice, you can't read it, sorry, the quality. Here the scale choice is related to the mass of the W boson, and what you choose here is a scale called HT, which is the sum of the transverse energy in the event. So you see that if you look at this, you would say, well, my perturbative expansion is not converging well at all. I have really gigantic negative corrections here. If you look at this here you see the ratio plot is essentially flat. You see the perturbative expansion really converges very well and corrections are small.
Sorry, this is which scale is this? The factorization scale is.
So here it's the W mass,
Yeah.
and here it's a
I'm saying
dynamical
the
scale.
scale is the factorization one. that
Both,
uses-
both are set to the same.
So which are the same? Factorization, the other
And
one?
renormalization scale for the coupling constant.
You said them are the same
Typically they are set to the same value and then vary up and down.
because I mean they don't have to be the
They
same.
don't have to be the same, no. In fact, if one wants to be a bit more conservative, you vary them independently. This is not always done, but you see that here, I mean, the fact is dramatic. So here you can say, okay, what is happening here is that you have large logs of your, essentially here you have a hard scale, ET divided by mu, your, in this case, small factorization scale. So the issue here is that you're going to very high energy, so you have a very hard scattering, but the scale that you chose here, MW, doesn't know about it. It doesn't become high enough. So somehow the leading order uses a too low scale, so alpha S is too large, and so the leading order is far too large here. So what is usually done? So, for instance, in this example, what people did is they observed that this is a bad scale choice and this is a much better scale choice. So a posteriori, you decide which one is a good scale, and then you can sort of motivate it.
So wait, the second case, the scale is not fixed.
No, each event has a different scale.
Yeah.
Yeah. So that essentially, if you're here, you have a hard scale. If you're here, you have a soft scale. So so-called dynamical scale choice.
It's up to 500 J.
This is up to 500 J.
And these are Monte Carlo predictions.
This is NLO, leading order NLO.
So there are no data to compare it to.
Yes, now there are data, but they are not here.
I'm just so busy, it's purely theoretical problem. In a sense,
Here, if you want, this is just to illustrate the problem. Yeah.
I mean, in principle, I don't even know whether QCD is correct, so the running of the coupling could change too.
Well, not 500 GV, not.
That is some discussion, but just.
No, okay, but now there are data, and in fact, one can see that this with this scale choice. So, you really, I mean, this scale was also then fine-tuned. It was divided by a factor 2. It was modified a little bit. Rather than the transverse energy of the W, you can take the sum of the leptons
So
and
these are
two things.
heuristic methods, basically. These are heuristic methods, basically. You just, a
Yeah.
posteriori check.
A posteriori check, and okay, so often the scale is chosen a posteriori. Why? Well, you know that if you have a bad scale, like the example before, you will generate large logs, so you will have very large corrections. On the other hand, we also know that the other direction is not true. You can have large NLO corrections that have nothing to do with having chosen a wrong scale choice. Right? So these NLO corrections can have a physical, genuine origin. For instance, in the examples that we discussed here, the fact that you can have new channels, or that you have some enhancement, color enhancement, and so on. The other thing is that whenever you change scale, whenever you evolve alpha S from one scale to another, you're generating what is called a single log. So alpha times a log of the ratio of the scales. Single log. In cross sections, there are double logs as well. So alpha log of ratios of scale squared. So whenever you try to absorb a double log into a single log scale choice, you're doing a mistake. And the other thing is that essentially, if you choose a scale in a physical way and then vary it, you can use it as a way to estimate your field uncertainty. if you choose a scale a posteriori so that things work, then it becomes very difficult to sort of use scale variation to estimate the uncertainty, because you choose a scale, for instance, in the example I was putting here, if you choose a scale where you are sitting in the plateau, and then if you vary the scale, nothing happens, so you would think that the fear uncertainty is very small, but it doesn't have to be, right? So you lose this handle on the theory error. The other issue with NLO calculation is merging to pattern shower. So if you do an NLO calculation, I showed you, even this more advanced, you have maybe 4 or 5 particles in the final state. At the LHC, you have maybe 30 or something like this. So you want to sort of still allow these particles to have final state radiation and hadronization. And this is something that in fact was understood now about 10 years ago. There are 2 main methods of how to do it. One is in MCAT NLO and one is in PowerHack. And now these tools, NLO and pattern shower, are really used by all advanced LHC analysis. And I mean, what was difficult is to understand, whenever you have pattern shower, essentially what you're doing is you take your hard event and you allow it to radiate soft radiation. But you don't want to double count what is already included in your NLO correction. This was the difficult thing. But now this is something that is really well under control. And the last issue is what is called the so-called merging problem that I would like to discuss a bit.
So can I just answer briefly, how do people avoid this double counting? I mean, what is the strategy to avoid it?
So there are 2 strategies, I think there are 2 methods. In this method here, you compute what is the double counting and you subtract it. And in the other approach, you sort of generate things in such a way that the hardest emission, so this is the hardest emission is from the NLO. And then you don't have issues of double counting.
So that seems sort of straightforward. Why didn't people do that before?
No, it's not straightforward.
straightforward.
No, it's not straightforward. No, by far not. In particular, so in this approach, what you do is depends a lot on, but in both approaches, there is a dependence on the pattern shower. So this approach really works in the PT ordered showers, and here what you subtract really depends on the shower that you're using. So it's
Yeah, okay, so you need for the last thing you need a PT order shower, which is not what PTA does, for example.
PTA has various versions, has also PT ordered.
Yeah.
Yeah. No, it was by far not straightforward, but once then. Now this merging problem. So what is this problem? Now suppose that you have different next to leading order calculations. So I compute Higgs plus jet, somebody else computes Higgs plus dijets, and this was the essence of time. So you have 3 different calculations that now are all in PowerHack. So they are actually at NLO plus pattern shower. Now these 3 calculations have different accuracies in different regions of Higgs space. So the pure Higgs calculation describes the first jet only at leading order because it comes from the real radiation. And all our jets then come from the pattern shower. If you take Higgs plus 1 jet, the spectrum of the leading jet is really described at NLO accuracy. The second jet at leading order accuracy, and all our jets come from the pattern shower. But you can't use this calculation to compute an inclusive Higgs cross-section if you don't impose a cut on the PT of the jet. Without this cut, the calculation is divergent, as you see somehow here or here. The NLO calculation diverges from there. And again, the Higgs plus 2 jet calculation has 2 jets at NLO accuracy, but diverges if you don't impose these 2 cuts on the both jets. Now, of course, it sounds very sensitive. It's actually to want to merge this calculation, to have one calculation that works everywhere. And essentially, it's also physical, it's very important, because often now what people are doing is, for instance, they look at Higgs cross-sections, imposing a jet veto. So it's something that is inclusive on the Higgs, but you want to veto on the jets. So if you impose a jet veto here, you are using this calculation, you're describing the jet only at leading order. So what is the standard procedure? How can you merge this calculation? What you can do is you can introduce what is called a merging scale. And then you can essentially say, okay, if my event is below or above this merging scale, I switch from one calculation to another one. Right, so if the jet is hard, I use Higgs plus 1 jet. If the jet is soft, I switch to Higgs with no jet. And the problem is that when you do this, you introduce essentially a dependence on this additional scale that you introduce, right? And also, practically, the choice is difficult. If the scale is too small, you will generate large logs. If the scale is too large, for instance, if you acquire 100 GeV, you are sort of only looking at this Higgs plus 0 jet, even to describe a jet at 100 GeV. So you don't want to do this. You don't want to have it to large scale, but you can't have it to soft scale. And just to show whether this matters or not, these are now numbers that I took from this talk here. You can look at, for instance, Higgs plus 0, 1, 2 jets with two different imaging scales. And you see that the composition in terms of these processes changes according to your merging scale. So if the merging scale is high, as I told you, you become totally dominated by Higgs plus 0, and here you have a large fraction of Higgs plus 1. So the composition changes, but then you can see, okay, if I look at the total, it doesn't matter. So I'm happy, it doesn't really matter. But this is with inclusive cuts. Now you change cuts, and to go to cuts that are actually important for these Higgs plus digit studies, vector boson fusion cuts, where the Higgs is typically produced by the scattering of two vector bosons. This is one of the crucial processes to measure the coupling of the Higgs. So these are the cuts that are actually more interesting than this. And then here you see that things actually really change. The cross-section changes a lot just because you change your merging scale. Right? So it can have a quite big impact. Now, what we did now 2 years ago was to develop this what is called MINLO method. MINLO stands for multi-scale improved NLO. And what you do is essentially you take an event. For instance, here you have 5 particles into the final state. And then what you want to do is you want to find the most likely branching history that happened. So the way you do it is you can think of clustering particles together using some jet algorithm. So you cluster two particles whenever they are close by in a phase space, or whenever one is, for instance, very soft. So here, if you would run sort of clustering on this, you would start merging what I called here 4, 5 into one particle. Then you would, for instance, merge these two together, and then you would merge these two together. And then you would have essentially PP going to 2 hard jets. Once you do this, once you have this procedure, when you do this merging, every time you have what you call a merging scale here. So what you can do then is to say, okay, here a branching occurred at this typical scale here. So what you're doing in this MINLO method is you assign scales according to this procedure in a way that is essentially decided once and for all, dynamical, and each scale is also so different. So you can have a scale that is very soft and then one that is very hard. So not all scales have to be the same. And the other thing that is sort of crucial that we then did is that if you think about this as a sort of probabilistic evolution, so you start from here and then go here and then branch, and then from here to here branch, you also should introduce a probability to evolve from here, for instance, to here, without any branching happening. And this probability is encoded into what are called Sudakov form factors. So you have local scales, and then you introduce always Sudakov form factors that tell you what are the probability to evolve from this to this, or from this to this, without anything else happening. The Sudakov form factors are essentially 1 minus the one gluon emission probability, and to all orders they become the exponent of minus the emission probability. So these are things that are always present in Barton showers as well. So if you take an NLO calculation and apply what is this MINLO procedure, the result, what is the result? Well, you have NLO accuracy, so the dependence is next to the node. In the Sudakov regions, so the regions where these things become soft or collinear, you have a sort of leading logarithmic accuracy. The procedure is very simple to implement. Once you know how to do it, it's straightforward. But the inclusion of Sudakov form factors is very important, because what this tells you is that your jet cross-sections, for instance, the Higgs plus 1 jet cross-section will become finite even without a cut on the jet. Right? So it then allows you to merge, if this calculation is then finite, what we showed then in this paper here is that in fact, not only you can make it finite, but you can make it finite in such a way that it's really NLO accurate even for inclusive Higgs production. So when you apply this mean law procedure, for instance, to Higgs plus 1 jet, you are NLO accurate also for Higgs production. So essentially the mean law, together with Pauheg, deals with these three issues of NLO calculation, gives a procedure to choose a scale, allows you to merge different calculations, and from Pauheg you get the partial.
Sorry, is that unique? I mean, could you imagine another possibility, or is, I mean, I can understand the procedure, but I don't understand. It shouldn't be unique, right?
So, no, there's nothing unique here. First of all, those scales are chosen dynamically in the sense that this is the hardness of the process. But again, you can vary the scale up and down by factor 2. So the pseudo-conform factors, on the other hand, must have a given form in order for this to be NLO. So the form of the pseudo-conform factor is arbitrary at higher orders, but the lowest order coefficients are then fixed.
So here is your arbitrariness is in the choice of the different scales for the different unification of the processes. So which technically gives you many more scales. So how do you choose that one?
Once again?
So if I to say I first combine 5 and 4, then I combine 5, 4 with 1, for example. So these have different scales in all of these.
Yes. So but then this process has different alphas. So
yes, I know, understand. No, but I mean, when does the algorithm decide which scale to unify what? I mean, so at this point you have multiple scales, not only one. So would you be sensitive to the choices of factor 2 in every single scale?
For instance, if this process, for instance, started at something like this,
Right.
What we would do is we would say this is alpha of mu1, 3 different scales.
Okay.
One can be very hard and one can be very soft, reflecting the fact that maybe this branching is soft and this is
No, I understand. But I mean,
and then you can vary them up and down and get a scale variation.
it's a naive question, so you already will answer me. But wouldn't I think that if I have 3 different scales and I have a factor for each of them which is arbitrary, I would propagate an error which is larger than choosing only one scale error?
Okay, so here you can do 2 things. You can vary them all together or not.
Okay, but if you do differently, then you will have a larger error.
But not too much at the end.
I
They are a
mean,
little
there is a
bit
naive
larger, but
question.
at the end sort of, usually the bend comes from when both scales are up and both scales are carried down. So this is usually what gives you the largest.
I see. But there is a systematic error that you add by basically declusterizing alpha, basically.
I don't know how to say it. So here usually you take
Just one,
the
plus
fixed
or
scale,
minus.
the central scale, and then you vary this between your whatever you call 2 mu0
Exactly.
and mu0 over 2. Here you have your scales that come from this procedure, and then each one you can vary it alpha independently or not. Practically, it doesn't make a big difference because the bend usually comes when all scales are up or all scales are down.
Also, this factor of 2, I think, is empirical, right?
This factor is completely conventional.
Can you keep a ratio on these 3 scales? Like mu3 is
Depends on the process.
1/10 of mu2, and mu2 is 1/10 of mu1.
What do you mean keep direction?
No, really not.
Yeah, such they are a geometrical series in a sense. If there is a fixed ratio between mu2.
Yeah, but there is no fixed ratio. It really
No.
depends on event by
The
event.
process, yeah. The process depends.
So it can be that the 3 scales are really all very similar. So they're always ordered somehow. The 3 is always the smallest, but they can be all very close if you have a real multi-jet event, all jets, and they can be the one is very large and 2 are very
So
close.
this is just basically the transverse momentum.
The transverse
of
momentum of the
this,
branching.
something.
Exactly. So this is really inspired, I should say, by what the CKKW procedure that essentially does the same thing at leading order. So this started as a generalization at NLO of the CKKW procedure. Yeah. Okay, now just an example, if you take this on one of these calculations, W, Z plus 2 jets, this is now compared to data. So this is W plus 2 jets, Z plus 2 jets, and you can, so this is the 2-jet calculation with this Miller procedure. Then you can look at the cross section for 2 jets, this is now our band obtained by Weyl in this case. And here, these points are in Atlas theta. So what you see is that, okay, it works also for higher multiplicities, but also it works for lower multiplicities really quite nicely. While in normal and in local calculation, you essentially can't, you don't have a number here, it's really just diverges. So here you see, in this case, I have to say, this is the only point that really has NLO accuracy, but what you see and what one can also understand is that you're getting a lot of the higher order corrections also in the other cases. Okay. Now, what one should say is that all this NLO and looking at high multiplicity final state was motivated by looking for new physics, I already told you. Now, if you look at Susie or Susie's searches, this is for instance Susie's searches, you see that you have already about an exclusion of 1 TeV energy scale. And for exotics, I would say about a few TeV. So somehow all this looking for physics directly was not very successful up to now. The other thing that one has to keep in mind from LHC is we know that the Higgs was discovered in this region here. This is a region which is very phenomenologically very nice because it's very rich. So you have the Higgs that decays into BB bar, WW. You can access a lot of decay modes for the Higgs. And so people then started looking at these various decay modes. And as I told you, once you know the mass of the Higgs, everything is predicted. So you can look for deviations from the standard model pattern. And what is happening now, or what happened, is that essentially there is no deviation, no sizable deviation. This is the prediction. You see everything aligns to your predictions.
Giulia, can I be precise in that? I mean, if you assume the standard model, it's perfectly correct. But,
Sure.
but in this, the only one that you cannot calculate the self-coupling of Higgs. So the fact that mass is proportional to the coupling, these measurements don't fix that.
The cipher, yeah, okay, sure.
So technically speaking, in order to prove the standard model to be correct, the first relation that first showed that the mass is square proportional to the lambda.
Yes, but
that,
this,
that is
no.
one you cannot.
That's
so
right.
Technically speaking, the Higgs could be because of both of what we know.
No, but what this tells you is that the BB and tau tau are compatible.
So the Yukawa sector of the standard model is reasonably close to the one you expect from
The Yukawa and the gauge.
And the gauge. But that does not again establish the Higgs as a standard model.
Sure. But what I'm saying is that you didn't establish a departure. So you didn't find that tau is here and B is there, or W is here and Z is there. This you
But on the
didn't
other hand, since the flavor sector worked so well before,
yeah.
perhaps this is not the most
It's
surprising
not
result,
surprising,
right? I mean, we know that the flavor sector from the precision data is a scale for the flavor sector we got 10 to the 310. Then perhaps it's not the most surprising result of LHC because it was working well already before, extremely well from the flavor at all.
Sure. Yeah.
So
I
they say
agree.
this is perfectly fine.
I agree.
At least it's
Well,
nice to see.
It's nice. So the reason I showed this plot is also to sort of show what is the precision now. And what will happen in round 2 is that people will try to really improve now this precision very much. So you want to still sort of constrain this as much as possible. And so the point I want to make is that essentially up to now direct searches have not been successful. Indirect searches have a higher reach because everything that is loop induced and affects the couplings and so on, you have a sort of, because you produce new physics data indirectly, you have a higher mass reach. So I think that in the next run, it will become now more important to focus on indirect searches, but those, essentially because in direct searches you typically can have maybe mass peak or so on. Here, in this type of searches, indirect searches, you don't. So you really need much higher precision. So NLO is typically not enough. You want next to next reading order. And here, up to 2 years ago, all we had in next to reading order was Higgs and Giulia. That's it. Now, in the last 2 years, has been really sort of a remarkable process. TT bar, WW, WZ, Higgs plus Z, IZ. So many things are now being computed in next to next reading order, and those will be important for this type of indirect searches. At NLO, we saw that NLO went hand in hand with the development of NLO and Pato shower. So now, one should wonder, what about next to reading order and Pato shower? Of course, this is essentially mass, because you have your highest perturbative precision, and you have the benefits of having your hadronization mode, the exclusive description, and so on. Now let me give you you an example. So, in the case of Higgs production, these are essentially the elements that enter a next to leading order calculation. So you have this one, what I had already here, at 0, 1, or 2 loop. This at 0, 1 loop, and Higgs plus 2 partons at 3 level. Now, if you take this 6 plus 1 jet calculation in PowerHack, schematically drawn here, you see that you have already this at 0, 1 loop, and you have this at 3 level. And I told you that if you upgrade this with Millo and with the pseudo-conform factors, what you can do is you can essentially get also those at 0 and 1 loop. So you're almost done, right? You still, what you're missing is still this double virtual correction only. So this is also sort of summarized again in this table here. So Millo gives you this sort of merged generator. So you have this at an LO, this at an LO, and this at an LO, inclusive one integers. And if you want something at next to reading order, the only thing you see there is a small difference here because you don't have the double virtual. This is simply not there at all. But you're almost there. So how can you now upgrade this to go into here? The observation is that for a simple process like Higgs, the Born kinematics is determined by the rapidity distribution. So if you compute your Higgs rapidity distribution next to reading order, and you compute it with this merged generator, and you take the ratio of those two, you see that you get something that is 1 plus order alpha squared. What this means is that if you take these predictions from this generator and reweight it by this factor, because this is alpha squared, it will not change your NLO accuracy, but it will give you the correct Higgs rapidity at next to leading order. So it essentially allows you to upgrade this to next to leading order. So now I'm running out of time. So let me just say that this was done, so this was the first NLO plus Pardon shower generator for Higgs production, and one can see how well it does by comparing to, for instance, analytic resummation that exists. This is, for instance, for the Higgs PT spectrum, or for the jet PT spectrum, and there's lots to learn from these comparisons. The same has been done recently also for the Rayyan. To do it for more complicated processes is still really quite difficult. Now, I think I'm running out of time, so let me skip this last and just go to the conclusions. Let me just say now, I think there are fantastic data from Run 1, and much more will come now next year, from in the next 3 years from Run 2 at LHC, and then even later. The field will advance faster by sort of trying to extend the reach of this experiment. This you can do by having more accurate predictions. You really want to have more precise and faster searches, and you get it by doing precision calculations. At the end, I think the aim is to give the best picture at the end of the run of what has been really discovered, what has been really excluded in the best possible way. And this is, of course, important now also in terms of planning future colliders. Now, the progress in QCD in the last 10 years was really remarkable. We know now how things that were unthinkable 10 years ago. For instance, fully automatic next to leading order, NNLO for all 2-to-2 scatterings, and also merging and matching the NNLO and Pardon shower. Now, most of this process didn't come by just doing brute force calculation. It was really, many things were a lot about developing new ideas, new techniques. So I think it's a very exciting time, and it's a very nice time to do this type of calculations. And then stop.
Any questions?
I mean, it's beautiful to do more precise computations, but of course we prefer to see bumps, right? So this is, you know, I understand a lot of the reverse.
Who wouldn't?
Yeah, so the reverse psychology tactic.
No, but let me also say there were cases where there were bumps.
Yes.
You know, in the case of
Which
the
went away
Teleton,
because.
which went away because the bump came from backgrounds with different shapes.
Give me W2 jets.
Yes.
Yeah, no, I understand. But let me understand. So, assume that one of this program does the next reading order. So, in practice, how much we're going to improve on the cross sections? I mean, by how much we really gain?
Next to next,
Yeah.
comparing to next.
Exactly.
It's very process dependent. So if you take a single top, the next to next is essentially tiny, 1%. So if you want irrelevant, but it gives you sort of an idea that you really have quantitative control on this. You need to know this to really know that you have high
I mean,
precision.
that won't, I mean, but the truth is, you won't be able to tell me whether it's no physics, but just, I mean, if the, I'm trying to understand whether it's because I can do it, or whether I really gain something in doing it. And I want your honest answer rather than the political answer. And I mean, what would you say?
Now, if you have better theory predictions, what you can is you can push your exclusion bounds and so on, right?
But by how much?
It depends
Okay.
on what you're talking about.
But not by an order of magnitude in energy.
Not by a lot of
Pretty
things.
And of course also depends on the experimental.
Yeah, it depends.
precision,
Really
right?
depends.
Because if you have, so for example, for single top, what will the run to, and how will it measure single top production?
I don't know how well.
Presumably-
If it will compete with, I don't think so.
Sorry?
You mean if it will compete with the theory?
Yeah, exactly.
certainty? I don't
Presumably
think
not,
so.
no.
I don't think so.
Not-
In this
that would
particular
be
case,
much-
yeah.
okay.
But there are many other cases where
Sure.
theory certainty is
No,
much
I mean, there's of course also experiments, I mean, yeah.
I mean,
Yeah,
there are
you
many
think
things.
that-
For instance, in dijet productions, it seems that these NLO effects are very important. Now, dijet productions are input to Barton distribution function. So you want to measure the gluon distribution. And so if you can improve on the PDF fits, then this enter everything else again. So it's a lot of it.
Let me give a simple example. I mean, just let's play the devil's advocate. Let's say that the new color particle exists in this, hundreds of, 7 to 800 jobs. So then it also affects a very good percent, the computations, right? So it would actually mimic and next leading order production by just the fact that there is a color particle that you did include into the thing. So in that case, I will probably not be able to see, be able to actually mask the next leading order computation. So there's a logical possibility that this is correct to do it, but you won't be able to differentiate from a new object which is actually colored in that.
Mhm.
And that is anybody looking at that possibility?
I don't know.
Because it's,
No, but it's so. These are the difficult scenarios.
these are, of course, I'm picking at
Yeah.
I'm not picking the easy ones, but so the other question was so far this improves on the Higgs to glue group really. All this actually improves on the Higgs to
Mhm.
glue interactions, of course,
Mhm.
will do. But exactly for the self-coupling and the Higgs, the ones which we would really like to know, how much do we know, how much will we be able to say? Would these techniques help at all?
For
The self-coupling and the Higgs.
well, I mean, for instance, I showed you that there are this not an NLO, but NLO. You have now all the Higgs pair production things. Those are those that I know.
But those won't be improved again.
At the 13 TV run, no. This is something that will be relevant for future production. So once we're retired.
Yeah.
No.
Okay, so I just am trying to understand it after we get, from a model building point of view, let's assume that the flavor cycle is okay, looks okay.
Mm-hmm.
Then the only one left to actually, in the people's mind, to say that's an model Higgs, right?
Mm.
If one measures self-coupling, which is consistent with
So run 2 will not measure the self-coupling of the entities.
Not very good precision, or not.
Question. So do you have in this multi-scale method in Mingle, do you have problems with gauge variance?
Gauge invariance,
Yeah.
is there? No, we don't have problems, no. Why would there be? Now, all you're doing is,
But can you choose different scales for alpha and if you compute the amplitude?
the coefficient of the alphas is gauge independent, so you can do whatever you want with the alphas. You don't have, all you have to care about is that so essentially you have a Born term and then a low term, and you change the scales here as well. So by doing this, you affect this, and you have to make sure that you don't spoil the NLO. So you have to have a subtraction term for this, but that's all you need to care about. But gauge variance is.
And the renormalization for alpha is in a mass independent scheme?
It's a?
It's a mass independent scheme. It's an MS bar.
Yes.
Okay, so it doesn't. I mean, so the masses of the top as a persona is threshold. That's basically good by hand. They don't appear directly. Because you also have the. Yes. So in fact, it carries another question. I mean, the mass of the top is not well defined. So if you cross the threshold of the mass of the top, wouldn't that also introduce a systematical uncertainty?
Well, you do as you do for the other forks, when you cross
Yeah, but
cross
I mean,
the threshold. So
but
you
typically
are-
those are the mass of the pi. I mean, effectively.
Oh, for the D you have the same issue.
So they introduce a systematic uncertainty in all of this.
No, you change your beta function, there is a number of
No, but
things.
the error, the question is that there is an error on the masses of the top,
Top,
that also affects the threshold uncertainty. That's what I'm saying. So it introduces a systematic
So
an error.
this is
in that.
usually not taken into account.
Because I mean, the question is, to me, is always why did I know the next leading order, then I lose because I have other mistakes or other errors to propagate in other places. That will be also there. But that is only when you cross the
But I think this is completely irrelevant. I remember at some point I
maybe
had
it's
some
true, I
issues
don't know
with
that.
with
That
4
would
and
be-
5 flavors above the top range. So you can keep also 5 flavors above it. And you see that the difference is
That's
very
right.
tiny. So.
I need to have 20.
Hmm?
You need to have many. Really many times. Can I ask, is anybody else have questions? So far this is just for the standard model. So basically there is, as you were saying, like Naviga, where I can put a model and get the prediction this is not at that level. So which means that if I truly modify the standard model, I will not have this level of precision.
Depends. So what they're doing here in this framework is to really look also beyond this. So it depends on which
Process.
model. What do they? Yeah. No, the idea at some point is to have something homogeneous. Also, I mean everything at the moment is more for QCD corrections, but of course at some point there are also electronic corrections. If we talk about precision, then as well.